Hello everyone, my name is Abram and in today's video we will talk about resistivity. So let's get started. So in this particular video we will try to answer these three questions. Number one, what is resistivity? We will try to find out what actually resistivity is, right? Secondly, we'll talk about why is it called specific resistance. The other name of resistivity is specific resistance. We will talk about why it is called specific resistance, and the third point, where it is used. So what we can do with this information we will see in this particular video. All right, okay, so let's start with the first topic, that is what is resistivity. So basically what actually is your resistivity. Okay, so let me tell you, resistivity is the property of material, or in other words it's the characteristic property of material. Now let's, for a time being, let's look at what are the things that is like known to us, right? Okay, so for example, we know if we have a material, if that material is connected with a battery source, right, then what is going to happen, right? So obviously there will be a lot of electrons inside your conductor or the resistance or whatever you want to call it, right? So what is going to happen, these electrons, the moment it is connected with a battery source, there will be a potential difference across the terminals, right, or across the terminals here also. You can understand that, right? So the moment there is a potential difference across it, what is going to happen, there will be an electric field and these electrons will be drifted in the direction opposite to that of your electric field, right? So these electrons which are like inside the conductor, I'm talking about the free electrons here, right? So these free electrons which are like inside the conductor will be moving in that direction with drift velocity. So as they move, current will be there, right? So as this electron move, we all know there will be a current, right? And the current will have a direction opposite to that of the movement of your electrons, right? So if your electrons are moving in that direction, then your current will be in opposite to that of your electric movement. Yes or no? Right? So this is how your current will move, right? So we know, we have studied in our previous video, we talked about drift velocity, we talked about current, we do know the relation between drift velocity and current, right? So let's very quickly look at all those things, right? Okay, so we know drift velocity, relation between drift velocity, yes, the current is given as VDENA, right? So where VD is the drift velocity, E is the charge of your electron, N is number of free electrons per unit volume in that material, right? A is the area of cross section of the material. So you guys can see this is the material. This material has some L length, right? And it has an area of cross section of A. Is that a yes or no, right? Okay. Now, very quickly, we also know drift velocity is given as E, capital E upon M multiplied by tau, where E is the charge of your electron, right? E is the electric field which is like across this material, across this conductor, right, most probably, right? M is the mass of electron and tau is the relaxation time, right? So all you have to do is put this value here. We have already done this thing in our previous video. I'm just doing it so that you guys can just get a quick revision of what we already know, right? Okay, so I can be simply given as E, capital E upon M tau ENA, right? Pretty simple, right? Okay, so you can write your current as this, right? All right. Also, we know the potential drop across this particular material will be equals to V is equals to E times of L. Yes or no? This also we have done in the previous video. For all those who are not getting it, you guys can go watch the previous video and then you can understand this, right? Okay, so V is actually can be written as E times of L, and we all know the famous Ohm's law. So V upon I is a constant, that is your resistance, right? We have already studied about this. So by Ohm's law, all I have to do is just divide V upon I, and when I divide it, we know you always get a constant, and this value is actually equal to the resistance, right? We all already know that. So when I do that, you can simply see here, the electric field will be cancelled out, right? And you'll be left with resistance equal to, yes, M times of L upon E square tau NA, right? And we already know that your resistance is given as rho L upon A. Yes or no? So when I compare these two things, right, when I compare these two equations, so I can simply get rho can be given as, yes, m upon e square tau times of n. Is that a yes or no? Now what is your m? M is the mass of electron. Let me just write that here. Mass of electron, right? What is your E? Let me just write that here. E is charge on electron, right? Okay, what is tau? Tau is your relaxation time. Relaxation time. Okay, what is relaxation time? It's a time between any two successive collision, right? All right. What is n? N is number of free electron. Number of free electron per unit volume inside the conductor, right? So all of these things are defined. Now you have to understand, for a fixed, so Ohm's law states for any particular physical condition. So when physical conditions are set, that means you're not changing the length, you're not changing the area, you're not changing the temperature, you're not changing the pressure. So all of these physical conditions are same, are constant. So when that condition is satisfied, so you have to understand your rho is given as m upon e square tau times of n, right? So from this equation we can simply say that your resistivity is actually the property of material, right? Because tau, relaxation time, it's again the property of material. N, number of free electrons per unit volume, again the property of material. Mass, again the property. E square is again the property. So the only way you can change the rho is if you change the material. For example, so let's say I have a copper material. I'll just simply draw it here. Let's say I have a copper material. This is copper material. And let's say I have a material which is like made up of tungsten. So I have a copper material, I have a tungsten material, right? So obviously copper material, the atoms and the molecules are arranged in a specific manner, and it will be same for your tungsten material. The atoms and the molecules will be arranged in a very specific manner, but it will be different from copper. Is that a yes or no? So when I consider the rho for copper and the rho for tungsten, right? Let me just simply write it here. Rho for copper. So you have to understand m will be constant, e square will again be constant, but the tau, the relaxation time, will be different for copper as compared to that of your tungsten. Very similarly, number of free electrons per unit volume will be different for copper as compared to that of your tungsten, right? So the only way you can change the resistivity for a fixed physical condition is by changing the material, right? So when the material is changed, what is going to happen? The relaxation time changes, and also number of free electrons per unit volume also changes, right? So resistivity, I can simply say, so for every copper material, it can be big copper, it can be small copper. For every tungsten material, it can be a big tungsten wire or it can be a small tungsten wire. The resistivity of that particular wire or the material will be same, right? So that's why I can say it is a characteristic property of material. I hope that is understandable. Yes. Okay. If that is true, let's go to our second topic, that is why it is called specific resistance. Okay, it's pretty simple. We all know resistance is given as rho L upon A. Now let's imagine for a time being, I have a material here. So I have this material, right? Now this material is very special. Why it is special? Because this material has a length of 1 meter and it has an area of cross section of 1 meter square. Pretty strange, right? I have a material which has length 1 meter and area of cross section 1 meter square, right? So this is very special, right? So when you put the value, when you find out the value of resistance with this equation, so put the value of length as 1 meter and put the value of area as 1 meter square, you will get your resistance is actually equal to resistivity. From this equation you can see your resistivity is actually equal to the resistance. Can you guys understand this? Your resistivity is actually equal to resistance. Can I say a simple statement? I'm saying that your resistivity is actually resistance but under a certain condition. Yes, your resistivity is actually resistance but under a certain condition. Now what is that condition? Condition is you have to take a material of 1 meter length and 1 meter square of area. Right? Is that a yes or no? So I can simply say resistivity is a special case of resistance. Your resistivity is actually special case of resistance. So you have to understand your resistivity is resistant only, but a special case. What is the condition for that special case? Is that you need to find a material which is having, one length as 1 meter as the length and 1 meter square as the area of cross section. Is that a yes or no? So because of this special condition, we call our resistivity as specific resistance also. Why? Because the resistivity is actually equal to resistance under a specific condition. That's why we call it specific resistance. Is that a yes or no? Right? That's why we call it specific resistance. I hope that is understandable, right? Let's look at the units here. So resistance, we already know resistance is given as rho L upon A, right? We are supposed to find out the unit of resistivity, right? Now resistance as a unit of ohm, that is your omega, right? Rho we have to find out, right? Length has a unit of meter. We are talking about SI units here, right? And area has a unit of meter square. So this meter and meter square will cancel out. You will get rho will be having a unit of ohm meter. I hope that is understandable. Yes. Okay. If that is true, let's move to our third and the last part, where it is used. Now you have to understand that we just heard that your resistivity is actually resistance, right? So more the value of rho, or I can simply say more the value of rho, that simply mean more the resistance offered in the flow of electron, right? So if the value of rho is more, that simply mean that material will be giving more resistance in the flow of your current. Is that a yes or no? Right? So if material with low rho, for example, you have a material which is having a low resistivity or low rho, so that material will give less resistance in the flow of your current, right? And that's why we call those materials conductors. Is that a yes or no? Right? Makes sense, right? If your rho is higher, the resistance will be higher, right? For that 1 meter length and 1 meter square area, material, right? So if your rho is higher, resistance is higher. So if your rho is higher, resistance is higher, that material will be insulator, right? It will not allow your current to flow easily. Is that a yes or no? Very simple. So materials with low rho will be considered as your conductors, and the materials with high rho will be considered as your insulators. So where we can use this information? We can use this information to find out whether your material is a conductor, semiconductor, or an insulator. So the materials which are having high values of rho will not be conducting materials. They will be most likely insulating materials. So the materials which are having low rho will be your best suited for conductors. Is that a yes or no? So I have a simple table from your NCERT book. So we have here materials, and we have here resistivity in ohm meter at 0 degrees Celsius. Temperature is fixed. So we are talking about the resistivity of the material at a fixed temperature, that is your 0 degrees Celsius, right? So you guys can see you have 1.6 into 10 to the power minus 8, right? Minus 8 ohm meter, right? So they are in like points, right? So these values are in points. So the less the value of resistivity, they will be considered in the conductor section, right? So you guys can see these are the most common conductive materials, and these all have less value of your resistivity, right? Very similarly, as we go to semiconductors are those material which have intermediate property of that of your conductors and that of your insulators, right? So you guys can see they will be having slightly more value of your resistivity as compared to that of your conductors, right? On the other hand, to the bottom of the table, you will see your insulators which have high values of resistivity, right? They have very high values, 10 to the power 10, 10 to the power 14, right? So glass has a resistivity of 10 to the power 10 to 10 to the power 14, very high. Your water, pure water, has a resistivity of 2.5 into 10 to the power 5, very high resistivity, right? So because of these high resistivity, they are very bad conductors of electricity. I hope you guys can understand that, right? Okay, very good. So one of the most famous question that always come from this topic is, let me just read that out and let's try to do this together, right? You guys can pause the video and just do it with me. A wire of resistance R is stretched to double its length. What will happen to its resistivity and resistance? So you have a wire and you have stretched that wire so that its length can get double, right? So when you double the length, so basically the material is same. You have to understand. So if I had a copper wire, so I'm stretching that copper wire, right? So I haven't changed the material. So if you haven't changed the material, the resistivity will not change. You have to understand that, right? So copper wire, again, after stretching also, the wire is still copper, right? It is still made up of copper. So as you have not changed the wire, the resistivity of that wire will be same. Let's try to find out what will happen to the resistance although, right? Okay, so you have, let's say I have this wire. So I had this wire. So you have stretched this wire to make it bigger, right? So obviously when you stretch it, the area of cross section must have been reduced, right? So let's say initially the length was some L and initially the area of cross section was some A, right? So now it is given in the question that stretch to double its length. Now the length is now double, 2 times of L, right? Now we do not know what happened to your area, right? But we know the volume at the initial part and at the final part will be same, because obviously we have a fixed material, right? So from that material we are changing or we are making something, right? So the volume over here will be equal to volume over here. Is that a yes or no, right? So I can simply say volume can be written as A times of L will be equal to, here I do not know the value, let me call it question mark as the area, multiplied by 2 times of L. So from here I will get the area here, right? So question mark will be equal to A times of L upon 2L, L will cancel out. So now the new area will be A by 2. Can you guys understand? New area will be A by 2. So this will have an area of A by 2. Right now I have the area, I have the length of this new, stretched wire. All you have to find out is resistance. The resistance is given as R is equals to rho L upon A. Just put the value. Rho will be same, right? Length is 2L now and area is now A by 2, right? So area is A by 2 and this can be written as, this is rho L upon A times of 4, right? And this is the previous resistance of the wire, right? So let me just say R dash is the new resistance and R is the previous resistance. So you can simply say R dash is equals to 4 times of R. So your resistance will be increased by 4 times. Resistance will be increased by 4 times. What will happen to resistivity? Resistivity will remain same because we haven't changed the material, right? And we'll just simply assume that we were talking, we haven't changed the temperature, right? Temperature is like, let's for the time being, let's say the temperature is actually constant for this particular question. I hope you understood this, right? I hope you understood the concept of resistivity. I hope you understood what is resistivity. I hope you understood why we call it specific resistance and where we can use this information, right? I hope that is understandable. If you have any doubt, you can comment it down in the comment section. And that's all for today. Thank you and have a nice day.